All right, in this video here, we're going to talk about rational exponents, which means a fraction as an exponent. Right. So before we even get into the definition of a rational exponent or what it means, let's think about what does that even mean. Right. We know that exponents mean repeated multiplication. So if I had like 9 raised to the third power, that would mean 9 times 9 times 9. Right. 9 multiplied by itself 3 times. Well, what if I had 9 to the 1/2 power? How do I multiply 9 by itself 1/2 times? Like, what does that even mean? It doesn't seem to make much sense at all, does it? Right? But still, we have rational exponents, right? They exist. You can raise a number to a 1/2 power or to a 2/3 power or something like that. So let's just try to figure out what this is, and then we'll look at what the actual definition of it is. Right? So 9 to the 1/2 power, I don't know what that equals, but it's got to equal something. So let me just say it equals x. And then we'll try to figure out what x is, and we'll go from there to try to figure out what that meaning of the 9 to the 1/2 power is. Right, so if 9 to the 1/2 power equals x, and I want to figure out what x is equal to. All right, so we have to be a little bit, clever here to figure this out. If I have 9 to the 1/2 power, something I can do with that, if I go back to the rules of exponents, or the laws of exponents, if I have 9 to the 1/2 power, and I square that, well, I'm allowed to do that as long as I square both sides of the equation, right? I'm working with an equation now, so whatever I do on one side, I have to do the same thing on the other side. So I'm going to square both sides of the equation. And the reason I do that is because what I've created here is a power raised to a power, right? And when I have a power to a power, according to the laws of exponents, I multiply those two together. So what is 1/2 times 2? Well, 1/2 times 2 equals 1, right? So this gives me 9 to the first power equals x squared, right? And that's the reason I chose to raise both sides to the second power, is because I knew when I did the power to a power and I multiplied that the 2 would cancel out that 1/2, right? So I raise both sides to the second power, I get 9 to the first power equals x squared. So if 9 to the first power equals x squared, and 9 to the first power just equals 9, right? Right, so what number squared is going to give me 9? Well, 3, right? 3 squared equals 9. Right, so x here equals 3. Right, so what I'm saying then is 9 to the 1/2 power equals 3. Right, makes sense, because if I square both sides, if I do 3 squared and 9 to the 1/2 squared, I get 9 equals 9. All right, so what does that tell us then? That 9 to the 1/2 power equals 3. All right, that's great, but do I really have to do something like this every time I have something raised to a 1/2 power? Is there like a simpler way we can do this? Think about it like this. What is the relationship between 9 and 3? Like if I start with 9, what do I have to do with 9 to get 3? Well, if I take the square root of 9, that gives me 3. Right? So 9 to the 1/2 power equals the second root, or the square root of 9, which gives me 3. Right, so based on this, a rational exponent, right, a fraction in the exponent actually corresponds to a root. Right, 9 to the 1/2 power is really the square root of 9, which equals 3. So that's really what a rational exponent is. It's another way of talking about a root. All right, and I'm going to pause this here and then put up the actual definition of a rational exponent. All right, so we saw here that the 9 to the 1/2 power equals the square root of 9, which is 3, because 3 to the second power equals 9. Right? So the definition of a rational exponent, a to the m over n. Right? Remember, rational means a fraction. So if my exponent is a fraction, m over n, that's equal to the nth root of that base a raised to the m power. And that m power, there's actually 2 different ways you could write this. You could put that m power outside of the root, or you can put that nth power on the base number a inside the root, right? There's 2 different ways that can work, right? So just like we saw here, 9 to the 1/2 power, that was the second root, right? So whatever the denominator number is, that's the root that you're taking. Whatever the numerator number is in your exponent, that's the power that you're raising it to, right? Since this one was 9 to the first power, I didn't write that 1 there. We have the 1 up here, right? So this is the second root of 9 to the first power. That's 9 to the 1/2. All right, so a to the m over n power equals the nth root of a raised to the m power. All right, so when you are dealing with rational exponents and you're trying to evaluate what a rational exponent is, usually the easiest way to do that is to change it into a root and then you can do the calculations that way, right? Trying to just look at 9 to the 1/2 power, like, well, what is 9 to the 1/2 power? But if you change it to the square root of 9, well, then that's pretty easy to figure out that the square root of 9 equals 3. Right, so when you're trying to evaluate rational exponents, usually you change them into the root form, and then you can evaluate them and figure out what they're equal to. All right, so that is the definition of a rational exponent. And when you're changing it from one form to the other, the basic rule of thumb is whatever the number in the bottom of the fraction is, that's the root that you're taking. And then, so that's the number that goes in that little nook, that index spot of the radical, right? So the denominator is the root that you're taking. The numerator goes up higher. So the higher number here, the one that goes up above, right? The one on top of the fraction, stays up above. That becomes the exponent here or the exponent there. No matter where you put it, that m, that numerator number from the exponent, is your exponent when you are changing it to the radical form. Okay, I'm going to erase this one up here and then put up a couple examples of working with this definition of the rational exponents. All right, a couple examples here involving rational exponents and just doing basic computations of numbers that involve rational exponents. Right, so the first one here is 4 to the 1/2 power. All right, I left up here the definition of a rational exponent. Right, so if I have 4 to the 1/2 power, remember when I'm changing that to the radical form, maybe I can draw that a little bit better there. When I'm changing it to the radical form, whatever the denominator of my fraction is, the 2 in this case, that's the number that goes in the root. So I'm taking the second root, or the square root here, whatever the base number is, goes inside or underneath the radical, and then I take that whole thing and I raise it to the power that's in the numerator of my fraction, in this case a 1. Right? So 4 to the 1/2 power is the same as the second root of 4 raised to the first power. Right, again, the base number, the denominator number goes in the little nook there. That's the root that you're taking. The numerator number becomes your exponent. Right, and it's always that same way when you're switching from one form to the other. It's just one of those little patterns that you have to get down and be able to do. All right, so what is the second root of 4? Well, the square root of 4 is 2. Right, and 2 raised to the first power still equals 2. Right, so 4 to the 1/2 power equals 2. Right, so whenever you see a 1/2 power, the example I had up here before of 9 to the 1/2 worked out kind of the same way as this. A 1/2 power just straight corresponds to a square root. Right, so 4 to the 1/2 power is the square root of 4, which equals 2. The one we had before, 9 to the 1/2 power, was the square root of 9, which equals 3. If I had 100 to the 1/2 power, that's going to equal 10, right? Because the square root of 100 is 10. Right, so the 1/2 power is just the square root. It's just another way of writing the square root. All right, 8 to the 2/3 power, a little bit more complicated because now my fraction doesn't have a 1 in the numerator. And also I have a denominator other than a 2, so it's not going to be a square root this time. All right, so if it's 8 to the 2/3, I set up my radical. The denominator, the 3, that's the root I'm taking, so I'm taking the third root of this base number, 8, and then I have to raise that whole thing to the numerator number, the second power. All right, so 8 to the 2/3 power corresponds to the third root of 8 to the second power. All right, so now I have to figure this out. So what is the third root of 8? All right, well, the third root of 8, what number multiplied by itself 3 times gives me 8? Well, that's going to be 2, right? 2 times 2 is 4. 4 times 2 gives me 8. So 2 to the third power equals 8. So this is going to be 2 squared, which is going to equal 4. All right, so 8 to the 2/3 power equals 4. All right, I hope that made sense. I take the rational exponent, I change it into the root form. Again, it's always the same pattern. Base number goes under the radical, denominator goes in the nook, numerator goes in the exponent. Figure out that radical there if you can, the third root of 8, which in this case was 2, then raise that to that exponent 2, and in this case we get a 4. All right, the last one we have up here, 125 to the negative 1/3 power. All right, well, first thing, I have a negative exponent. So the rules of exponents tell me that I need to take the reciprocal of this. This is 1 over 125 to the 1/3 power. Right, now, when I do the reciprocal of this, you know, my exponent itself is a fraction. So when I see that negative exponent and the exponent's a fraction, I don't just flip over the fraction and make this 125 to the 3rd power. I have to take this entire thing and take that 125 to the 1/3 and put that in the denominator. Right? That's another common mistake I see people make and say, oh, it's a negative exponent, I need to flip over the fraction, so let me make that 125 to the 3 over 1. right? That's not how it works, right? You don't flip over the exponent itself, you flip over the entire expression. Your base number goes in the denominator. Your exponent stays the same, except it now becomes a positive 1/3 instead of a negative 1/3. All right, so it's 125 to the, or 1 over 125 to the 1/3 power. And now I can write that 1/3 power as a radical, right? So the base number 125 goes underneath the radical. The denominator, the 3, is the root I'm taking, so I'm taking the 3rd root. And then the numerator of my exponent, the 1, becomes the exponent on that whole radical. So it's 1 over the 3rd root of 125 to the 1st power. Right? Same thing I did for these first two up here. It's just this time, since it was a negative exponent, I had to flip it over. So now that radical is down in the denominator. All right, but then I can figure it out. What is the 3rd root of 125? What number multiplied by itself 3 times is going to give me 125? Well, that's going to be 5, right? 5 times 5 is 25. 25 times 5 again is 125. So it's 1 over 5 raised to the 1st power, which is just going to be 1/5. Right? So 125 to the negative 1/3 power equals 1/5. All right. So that is, or those are a couple examples of doing some computations with rational exponents. I'm going to pause this again and put up a couple more examples where we kind of deal with the laws of exponents with rational exponents. All right, so actually I just put up one more example here just to show you that the laws of the exponents, which we talked about on another video, they still apply to rational exponents, right? Those laws of exponents, they don't care if your exponents are whole numbers or positive or negative numbers or fractions or decimals. The laws of exponents are what they are. They apply no matter what type of exponent you have, right? So this example here, a to the 2/5 times a to the 7/5 over a to the 3/5. Well, I have a bunch of a's here as my bases being multiplied and divided. So the first thing I'm going to do is clean up the numerator, right? And if I have two things with the same base being multiplied together, I have to add the exponents. All right, so I have to add 2/5 plus 7/5. Which let me just kind of go off on the side over here. 2/5 plus 7/5 equals 9/5. So that's going to be a to the 9/5 over a to the 3/5. Right? Just like if it was a to the 3rd times a to the 4th, I would just add them up and get a to the 7th power. Well, just because those exponents are fractions, it doesn't change what that law of exponents says to do. When I multiply the same base, I add the exponents. And remember, when you're adding fractions, they have to have a common denominator. Lucky for us in this example, all of our denominators are 5, so we don't have to worry about finding common denominators. But if this one was like 2/5 and this one was like 7/4, you would have to get a common denominator before you can actually add those together, right? So remember, the rules of dealing with fractions also don't change now that we're dealing with exponents, right? Still, for adding fractions, you find a common denominator and then you add the numerators. If you're multiplying fractions, you still just multiply it straight across. You know, those rules for dealing with fractions are what they are no matter where those fractions come up or what type of problem you're doing. All right, so for this one, we multiplied those two up top, we added the exponents, we got a to the 9/5 over a to the 3/5, and now we have the same base, but being divided, which means we have to subtract the exponents. All right, so I have to do 9/5 minus 3/5, and if I do that, 9/5 minus 3/5, well, once again, my fractions have a common denominator, which means I can proceed with my subtraction. I just subtract the numerators. 9 minus 3 gives me 6/5. So I end up with a to the 6/5 here. All right, so again, the purpose of this example was just to show you that, you know, even if we have rational exponents and we have to do one of these types of problems like we did with the laws of exponents, the laws of exponents are still exactly the same. It might be a little bit more difficult now because now you might have to add fractions and get a common denominator or go through the rules of multiplying fractions and things like that. But the laws of exponents don't change, the rules of fractions don't change. Even when you put them together, they're still the same. Right? So it's another key thing to keep in mind. A lot of times people get to something like this and say, oh, I have to use the laws of exponents and I have to do stuff with fractions. I give up because that's just too much. Right? If you know how to deal with fractions and you know the laws of exponents, it's not too much. You just have to be careful and make sure you do each part of it correctly. Right? That's it. All right, so that's the video on rational exponents. Right? Rational exponents are roots. They're also exponents, so the rules of exponents apply to those as well.